Hello, everybody, and happy Friday. It's about 12:46 p.m. and I'm feeling a little bit better, good enough to make a little video. So what I want to do is make up for the video lecture I missed on yesterday because I was sick. So this is going to be a relatively short, maybe half-hour video introducing everything you need to know in Chapter 10. And in fact, I will cover almost everything you need to know in Chapter 10 in this lecture. So let me just say I spent a lot of time on chapter 9, probably more than I needed to, but the reason was everything that we're doing in chapter 9 is going to be applicable in chapter 10. So I spent a lot of time talking about work and external forces and internal forces and the environment and the system and things like that. Everything is still going to come into play. So let's take a look at what's going to be important in chapter 10 and what you do not need to worry about. So Chapter 10 is all about interactions and potential energy. So one thing I wanted to talk about real quick about potential energy is a single object cannot have potential energy. It's always an interaction between two different objects. So for example, if I want to use gravitational potential energy, I have to include the Earth as part of the system because gravitational potential energy is really the interaction between the Earth and another object. So there's two kinds of potential energy that we're going to look at. We're going to look at gravitational potential energy and elastic potential energy or spring potential energy. Gravitational potential energy is the interaction between the Earth and an object in an elevated position. Elastic potential energy is the interaction between a spring and an object connected to the spring. So let's just quickly look at what I'm going to be covering in chapter 10, what you're responsible for, and what you don't need to look at or worry about. So one, the big thing in this chapter is the energy principle. And the energy principle, and in fact, this is the one equation that we're pretty much using the entire chapter. Everything revolves around this equation. So if you remember from our energy principle from chapter 9, we basically just said the work done by all external forces is the change in energy of the system. And in chapter 9, we only looked at two forms of energy. We basically looked at kinetic energy, energy of motion, and thermal energy, which is basically heat. We weren't looking at gravitational potential energy or elastic potential energy because we weren't looking at interactions. Now we're going to start looking at the interactions between the Earth and an object, the spring and an object. So now we have four different forms of energy we're going to be considering. We still have the work done by all external forces. So keep in mind, this is the work done by all external forces. So remember, you get to define the system however you want. Anything that's not the system is the environment. Any forces the environment exerts on the system will change the overall energy of the system, and it can change the kinetic energy, the potential energy, the thermal energy, or some combination of all three. So this work done by external forces is the sum of the work done by all external forces, and that results in the energy of the system changing. So the system now, once we start looking at interactions, four different kinds of energy we're going to look at. We've got kinetic energy, which is energy of motion. We've got gravitational potential energy, energy of an object in an elevated position. If there's a spring in the problem, we have elastic potential energy. So a spring can be stretched or compressed, and that spring stores energy. And then last but not least, if there's friction or air resistance, we can have thermal energy being generated. So I'll talk a little bit about the difference between conservative and non-conservative forces. Real quick, in Physics 4a, there's only two conservative forces you're going to see, gravity and elastic potential energy, the spring force. In Physics 4b will be another form of potential energy, and that's the potential energy between two charged particles. So if I have like two electrons next to each other, those electrons, because of their positions relative to each other, will have what's called electric potential energy. And then if I let the electrons go, they're going to repel each other, start moving away, and that potential energy is going to get converted into kinetic. But for Physics 4a, two forms of potential energy only we're looking at, gravitational potential energy and elastic potential energy. So gravitational potential energy, we'll go through very easy. it's just equal to the mass of the object in kilograms times g, 9.8 meters per second squared, times the elevation in meters. And one thing that's going to be important for this is you can define y equals 0 anywhere. In essence, you're just defining your origin. And the reason it doesn't matter where you define y equals 0, because all that really matters for potential energy is how much the potential energy changes. And if an object falls 1 meter, it doesn't matter where I define my origin, the change in potential energy is always going to be the same. Elastic potential energy is the energy a spring has when it's stored or stretched or compressed. And that equation we'll see is 1/2 k times delta x squared. Let me write that again. Elastic potential energy, the equation is 1/2 k, which is the spring constant, times delta x squared. Conservation of energy, real quick. So one, energy bar charts, I'm not going to cover. Read on your own. You may have a conceptual question on that in a quiz, but I'm not going to ask you in terms of solving actual problems using it. Energy diagrams, don't worry about, we're not going to cover. And force and potential energy, I'm not going to cover. Now, in terms of just conservation of energy, it's still this equation where the work done by all external forces equals the change in energy of the system. Conservation of energy just says if the total work done by all external forces is 0, which we call an isolated system because it's not being acted upon by the environment, or at least it's not getting energy transferred into or out of it. So if the work done by external forces is 0, then what we know is the change in energy of the system is 0. And that's basically what conservation of energy says. It just says that if I'm not transferring energy into the system or out of the system, the energy of that system doesn't change. Now, it can be transformed from kinetic to potential and back and forth, but the total amount of energy doesn't change. So that's a real big preview. Let's go to this in a little bit more detail. So again, just to remind you, our energy principle is we've got a system. You get to define that system. Within the system, energy can be transformed from one form to another. So it can be going from kinetic to gravitational potential to spring potential to thermal energy. But if the system is not being worked on by the environment, so the environment's not doing any work, the energy of that system doesn't change. But if the environment does work, then that work will transfer energy either to the system or out of the system. If the work is positive, energy is transferred to the system. If the work is negative, energy is transferred from the system. So the total energy of the system changes by the amount of work done on it. And let me just erase that because it's blocking the other equation. Your book, just so you know, just sort of combines the elastic and gravitational potential energy into one term, but it's really two separate terms. So our big equation again, the work done by external forces equals the change in energy of the system. And that can result in the kinetic energy changing. That can result in the gravitational potential energy changing. That can result in the elastic potential energy changing and in the thermal energy changing. So we just need to be specific in how we define our system, and that'll let us know whether or not we can use gravitational potential energy or elastic potential energy or even thermal energy. So I'll kind of write this down in a second, but if I'm going to include gravitational potential energy, the Earth has to be part of the system. If I'm going to include elastic potential energy, the spring has to be part of the system. And if I'm going to include thermal energy, all objects that heat up have to be included in the system. Okay, so important concepts. Now let's go to lecture notes. Okay, so again, and I'll probably say this 3 or 4 or 5 times, here's our big giant equation. The work done by all external forces on a system equals the change in energy of the system, which equals the change in kinetic energy plus the change in gravitational potential plus the change in elastic potential plus the change in thermal energy. We've already had two of the equations for energy. Kinetic energy, 1/2 mv squared, 1/2 times the mass in kilograms times the speed in meters per second squared. We've had an equation for the change of thermal energy. Now note, we don't have an equation for E final. We don't have an equation for E initial. We generally don't know how much initial thermal energy an object has, or even how much it ends up with. But we do know how much the thermal energy changes. So we only have an equation for the change in thermal energy. And that's equal to the force of kinetic friction times the displacement over which it acts. The two equations we haven't had so far are gravitational potential energy, mgy, and elastic potential energy, 1/2 k times delta x squared. Okay, so going through, here we go again. Work done by all external forces equals the change in energy of the system, which is the change in kinetic energy plus the change in gravitational potential plus the change in elastic potential plus the change in thermal energy. So let's just talk a little bit about the two different kinds of forces we're going to be looking at. So one, forces are generally classified into two kinds. One is called a non-conservative force. And the easy definition of a non-conservative force, it could be a little bit lame, but it's the definition. Any force that's not a conservative force. If it's not a conservative force, it's non-conservative. And in fact, every force that we've seen so far is a non-conservative force, except for gravity and spring force. A conservative force pretty much has two main properties. The first one is the work done is path independent, meaning it doesn't matter how the object got from its initial position to the final position. The work done is only going to depend upon the initial and final positions, not how it got there. So for example, for gravity, if I have an object here and I just lift it up a certain height, gravity will do a certain amount of work, and it doesn't matter if I lift that object straight up or if I move the object in some kind of weird path. As long as it starts and stops at the same position, the work done by a conservative force will be the same. And the second big one for this chapter is you can define a potential energy for any force that's a conservative force. So we have a gravitational potential energy because gravity is a conservative force. We have an elastic potential energy because the spring force is a conservative force. And then once you get to 4b, the force between charged particles is a conservative force. So we have what's called electric potential energy. So here's the big thing. Here's how you define not the potential energy, but the change in potential energy. So change in potential energy for a conservative force is equal to negative the work done by that conservative force as the object goes from its initial position to its final position. So the definition of the change in potential energy for any conservative force is equal to negative the work done by that conservative force as the object goes from some initial position to some final position. So using this definition of the change in potential energy. So one, we're not defining the potential energy, but just how much the potential energy changes. And it's equal to negative the work done as an object goes from its initial position to final position. So we saw in chapter 9 that the work done by gravity is equal to negative mg times delta y. Oh, got that right here. Well, the change in potential energy is defined as, for gravity, negative the work done by gravity, which means that my change in potential energy is going to be negative mg delta y. So my potential energy, so where do I want to write this? Okay, so my change in potential energy is final minus initial, which equals mg delta y. The minus signs cancel out. My delta y is just mgy final minus mgy initial. So if final potential energy minus initial potential energy equals mgy final minus mgy initial, my equation for gravitational potential energy must be mgy. M, mass in kilograms. G, the magnitude of the acceleration due to gravity is always positive 9.8 meters per second squared. Y is the height in meters. So the big thing that you need to remember for potential energy, for gravitational potential energy, is you can define y equals 0 anywhere because only changes in potential energy are meaningful. Meaning, let's say an object starts here and it falls. And it falls a total distance of 1 meter. Well, its potential energy is going to decrease because the height is decreasing. And how much it decreases is going to be the mass times g times the decrease in height. How much the height decreases is always going to be 1 meter. It doesn't matter if I define my y equals 0 to be at the ground. Doesn't matter if I define my y equals 0 to be at a different spot. It's always losing the same amount of potential energy as it falls 1 meter. So all that matters is how much the potential energy changes, which means we can define y equals 0 anywhere. Okay, now in terms of elastic potential energy. In chapter 9, we saw that the work done by a spring was equal to negative 1/2 k delta x final squared minus 1/2 k delta x initial squared. And again, the change in potential energy for any conservative force, and now we're looking at the spring force, is negative the work done as it goes from initial to final position. So here, if I look at negative the work done by a spring, this minus sign drops out and I get 1/2 k delta x final squared minus 1/2 k delta x initial squared, which means our equation for elastic potential energy must be 1/2 k times delta x squared. K is the spring constant. This is wrong. It shouldn't be Newton meters. It's newtons per meter. And delta x is how much the spring is stretched or compressed from equilibrium. And that's really chapter 10 new stuff in a nutshell. So again, our big equation is the work done by all external forces equals the change in energy of the system. Now we're looking at 4 different forms of energy that can change. I've got kinetic energy, 1/2 mv squared. So delta kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. I've got gravitational potential energy, mgy. So my change in gravitational potential energy is mgy final minus mgy initial. I've got the change in elastic potential energy, which is 1/2 k delta x final squared minus 1/2 k delta x initial squared. And I've got the change in thermal energy. So I don't know the initial and final thermal energy, but I know the change in thermal energy is force of kinetic friction times the displacement. So here are 3 big things in terms of defining your system that you need to keep in mind. And in essence, gravitational potential energy, elastic potential energy is an interaction between 2 or more objects. Gravitational potential energy, well, let's just say 2 objects. Gravitational potential energy is the interaction between the Earth and an object, which means if I'm going to include gravitational potential energy, I have to have the Earth as part of my system. If I don't include the Earth as part of my system, then gravity is an external force that does work on the system, changing the energy of the system. If I do include the Earth as part of the system, then what ends up happening is gravitational potential energy is transformed into other forms, namely kinetic. A spring potential energy is always an interaction between a spring and whatever's connected to the spring, which means if I'm going to include elastic potential energy, the spring has to be part of the system. And then last but not least, if I want to include thermal energy, it's always going to be friction causing thermal energy to be generated, which means more than one object is going to heat up. In general, let's say I have an object sliding across the surface. The object is going to heat up. The surface is going to heat up. I have to include all objects that change temperature as part of my system. So if you're including gravitational potential energy, the Earth has to be part of your system. If you're including elastic potential energy or spring potential energy, the spring has to be part of the system. And if you're including thermal energy, all objects that heat up have to be part of the system. And that's kind of it in terms of new material. So let me insert one page template, blank. And let's do college ruled. Delete, get rid of that. Okay, so just a quick little summary. Change in energy of a system is going to equal the total work done on the system by all external forces, which are forces coming from outside the system being exerted on in the system. That change in energy can be a change in kinetic energy, can be a change in gravitational potential energy, can be a change in elastic potential energy, and it can be a change in thermal energy. So let's just kind of write this another way. So this is sort of the one big equation, but if I write this as the work done by external forces equals K final minus K initial, which is my change in kinetic energy, plus UG final minus UG initial, which is the change in my gravitational potential energy, plus U spring final minus U spring initial, which is the change in my elastic potential energy or spring potential energy, plus the change in thermal energy. Again, notice I'm not writing this as the final thermal energy minus the initial thermal energy because I don't generally know it. So what I want to do now is just put all of the initial values on one side, all of the final values on the other side, and we'll get a second form of this equation, which is useful. So moving all of my initial values over one side, what I have is the work done by external forces plus the initial kinetic energy plus the initial gravitational potential energy plus the initial spring potential energy equals my final kinetic energy plus my final gravitational potential energy plus my final elastic potential energy plus my change in thermal energy. So this is equivalent to that very first equation, where now instead of writing things as delta, I've specifically moved all the initial values to one side, all the final values to another side. And then if I want to just be completely clear in terms of the equations, I can write this out as the work done by external forces, and these are all forces outside this system doing work on the system, E plus 1/2 mv initial squared, my initial kinetic energy, plus mg y initial, my initial gravitational potential energy, plus 1/2 k times delta x initial squared equals 1/2 mv final squared plus mg y final plus 1/2 k times delta x final squared plus my change in thermal energy. So this equation is equivalent to the above equation, where I've just specifically written out every single term. So these four equations basically are all the same. It's all saying the work done on a system by things outside the system results in the energy of that system changing, which changes the kinetic energy plus potential plus thermal energy. And we have two different forms of potential energy. We have gravitational potential energy and we have elastic potential energy. And then just to add this very last piece, so if the work done by all external forces is equal to 0, and if that's the case, we say the system is isolated. Now, to me, I don't really like that phrasing. For me, an isolated system is one which is not having any forces acting on it at all. That's not the physics definition. An isolated system is one in which the total work done by all external forces is 0. It doesn't say there's no external forces acting on the system. It says the work done by all of the external forces adds up to zero. If that's the case, then the change in the energy of the system is just zero. So basically my final energy equals my initial energy. And energy is just being transformed from one form to another. So what I want to do is just one example problem. I want to do it a couple different ways, showing you that how you define your system does make a difference. So let's look at example problem 10.8. It says, what minimum speed does a 100-gram puck need to make it to the top of a 3-meter long, 20-degree frictionless ramp? So the situation is I've got a 20-degree ramp, and I have an object which has some initial kinetic energy, and I want to know how fast must it be moving to begin with to just make it to the top of a 3-meter long ramp. So 3 meters is the length of the ramp. So that's 3 meters, which means this height right here, keep in mind, here's my angle. Here is my hypotenuse. If I want y, this is the opposite side. So my y final, let me just define y equals 0 at the bottom. Keep in mind, anytime you're using gravitational potential energy, you can define the system, you can define y equals 0 wherever you like. In general, there's always going to be one sort of obvious choice. Well, two, either where you start or where you finish. So my y final is going to end up being 3 meters times the sine of 20 degrees, which ends up being equal to 1.03 meters. Now what I want to do is just solve this two different ways. One, I want to use gravitational potential energy, which means the Earth has to be part of the system. Second way, I want to not define Earth as part of the system and show you get the same answer either way. So let me make this a little bit smaller so I can use some space out here, and let me draw, let's just use red and a slightly smaller font. Okay, so we're going to do this two different ways. I'm going to do this part A, where I'm going to define my system. What is this? Let's define our system as the puck plus the Earth. So before I even do that, let's look at the forces acting on this puck. If I were to draw a free body diagram, I basically have normal force, which is always perpendicular. I've got gravity, mg, and that's it. There's no friction. Now, something pushed this to get it moving up the ramp, but we're looking at it as it's already moving. So some force caused it to start moving, but now we're looking at it after it's already moving. So the only forces acting are the normal force and gravity. And if you look, this thing is being displaced up the ramp. The normal force is perpendicular to the ramp, which means the work done by the normal force is going to be 0 because the angle between the normal force and the displacement is 90 degrees. So the way I've defined my system, the only work done by external forces is the work done by the normal force, which is 0. So going to our big equation is the work done by all external forces equals the change in kinetic energy plus the change in gravitational potential energy plus the change in elastic potential energy plus the change in thermal energy. So one, the work done by all external forces is 0, which means the change in energy of the system is 0. So one, there's no spring. So if there's no spring, you don't even need to consider elastic potential energy. And there's no friction and there's no air resistance, so no thermal energy is going to be generated. So what I basically have is the change in kinetic energy plus the change in gravitational potential energy is equal to 0. So writing this out, I have K final plus UG final equals K initial plus UG initial. Now, two of these terms drop out. Take 10 seconds. Which two terms are going to drop out and why? Well, this thing, we want it to just make it to the top of the ramp, which means it just makes it there and then comes to rest, which means my final kinetic energy is 0. And I define y equals 0 to be the height at the bottom of the ramp, which means its initial gravitational potential energy is 0. So what I get is the final gravitational potential energy it ends up with is equal to the initial kinetic energy it started with, or mg y final equals, oops, 1/2 m v initial squared. If I solve for v initial, I get it's going to be the square root of 2g times y final. And once I put all of that in, so I've got the square root of 2 times 9.8 meters per second squared times 1.03 meters. Get the square root of about 20. It's going to be less than 5. The exact answer is my initial speed is 4.5 meters per second. So if something has that speed, then it will make it just to the top of the ramp. Now, here's a cool little thing you can do just as a preview, or not as a preview, as a review. So I could have solved this problem using Newton's laws. I know the acceleration down a frictionless inclined plane is g sine theta. I know the total distance over which it's accelerating is 3 meters. So you could have also figured out, given the acceleration, given the total displacement, given the fact that it ends up at rest, you could figure out what it must have been moving to make it that distance and just end up at rest. So this was me solving this using the Earth as part of a system. Let me go to another, how can I do this? Oh, let me go to another page and then just do this. What problem was this? Example problem 10.8. In fact, let me just do that here. Come on, why can't I get down here? It's not letting me move down. All right, let's do that here. So this is 10.8 done another way. And in this time, I'm going to define my system as just the puck. So remember, I've got this puck, which is moving up a ramp. That's at 20 degrees. We want to know how fast it must be going. So after traveling 3 meters along this ramp, it ends up at rest. Now, the first time I defined my system as the puck plus the Earth, so I could use gravitational potential energy. Again, remember that the forces we have are the normal force and gravity, mg. And remember, the normal force was not doing any work because the normal force is perpendicular to the displacement. But now that I've defined my system as just the puck, the external forces are the normal force and gravity, right? If gravity's not, or if the Earth is not part of the system, then it's an external force doing work. So now when I look at the work done by all external forces equals the change in kinetic plus, oh, ha 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 ha. So if the Earth is not part of the system, I can include gravitational potential energy. So I can include that term. So going back, just like before, there's no friction, no air resistance, so no thermal energy is going to be generated. The problem doesn't have a spring, so I don't even need to include elastic or spring potential energy. So this reduces to the work done by gravity equals change in kinetic energy, K final minus K initial. Remember, the work done by gravity is equal to negative mg delta y. So what I have is negative mg delta y equals 1/2 m v final squared minus 1/2 m v initial squared. Again, I end up at rest So my final kinetic energy is 0. So what I get is negative mg delta y equals negative 1/2 m v initial squared. Solving for v initial, I get v initial is the square root of 2 times g times delta y, which once you plug everything in, my delta y again is still 1.03 meters, g is still 9.8, 2 is still 2. I still get 4.5 meters per second. So I'll do another example or problem or two like this where we define the system a couple different ways. So just quickly as a review, and then I'll be done with this lecture, is first time I did this, I included as my system both the puck and the Earth. Since I included the Earth as my system, I can include gravitational potential energy. What we ended up getting was that the work done by all external forces, which is the normal force in this case, equals the change in kinetic plus the change in gravitational potential energy. The normal force wasn't doing any work. What we ended up getting was that the final speed was 4.5 meters per second. Now in this second way I'm doing it, I'm only defining my system as the puck, which means now gravity is an external force doing work on the system, and I cannot include gravitational potential energy. So I need to look at the work done by gravity, but I have to get the same answer each case as long as I'm being consistent about what my system is, what's an external force, and whether or not I can use potential energy. Whew! Okay, that is it. On Monday, I'll kind of recap this, and then we're just going to do example problems for Monday and Tuesday. I literally have covered pretty much everything you need to know for Chapter 10. All right, that is it. Happy Friday. Have a wonderful weekend, and I hope to see most of you on Monday.